Okay, everyone, welcome to another PS Platypus lecture. Today we're going to be looking at gastrointestinal histology. So I know this lecture has come a little bit late, and that is completely our fault. It kind of slipped through the cracks. We had a couple of people messaging us saying, "Oh, you've forgotten gastrointestinal histology. We're already up to like renal, urinary. What's happening?" And we kind of realized that that was a mistake on our end. So apologies for that, but hopefully better late than never. We're going to be going through as many of the gastrointestinal histology things that you would have covered in your workshops, as well as just a couple of extra bits of information that I've managed to acquire from doing a couple of practice exams in second year. So without any further ado, let's begin. Now, it's really important before we even look at any of the organs to actually have a think about the general layout of the gastrointestinal tract. So the tract, what I mean by that is it's just a tube. If you think about it, it's a tube from beginning to end, so mouth to anus. The only thing that happens is that it inflates in some places and then it deflates in others. So classically inflates in the stomach, and then it just has various sizes of the lumen in different places. Obviously, that's not true, right? Like you've got changes in the structure of the actual layers. So you can have some glands in some places, others not so much. But in essence, it's all the same. So what you have is you have an outer layer. In this case, it's the innermost layer of the tube, which is the mucosa. So that's the epithelial cells. It has a lamina propria, which is loose connective tissue. It also has a very, very thin muscular sheet called the muscularis mucosa. Not that important for us to know. The main thing is that the epithelium, it's either stratified squamous or simple cuboidal most of the time. Stratified squamous is generally when it's required for protective purposes. So if there's going to be a lot of chafing or food going through, so it's going to scrape through. For example, if you have the early sort of like esophagus area, or you've got the lower part of the anus or the rectum, that's usually stratified squamous. The rest, when you have absorption properties or you've got secretion properties, that's more likely to be a simple cuboidal because those cells need to be a little bit bigger. Again, it's a very general rule, but it's an easy way to think about it. Submucosa, so that's the next layer that comes. So going from inside to out, just basically loose connective tissue. It contains the submucosal or Meissner's plexus. The muscularis externa comes next, or in this diagram, it's called the muscularis propria. In this one, it actually contains the myenteric plexus. I'm not sure if you've covered these plexuses before. I think they would have been covered in some physiology lecture. But for now, just know that they have these nerve plexuses there. And the interesting thing to remember is that the myenteric plexus is sandwiched between the circular muscle layer and the longitudinal muscle layer. And then finally, on the very outside, you've got serosa, or you've got adventitia. So serosa, as you know, like the serous membranes. So these are the mesothelial layers that cover organs that are suspended within either the thorax or the abdominal cavity. If an organ is attached to another tissue, though, so if an organ is directly attached to another organ, or it's attached to the posterior abdominal wall or something like that, then it's going to be covered more by adventitia. Again, you don't need to know the difference, but the main thing is you've got serosa or adventitia on the outside. A really dumb mnemonic that I came up with, because I always forgot this, is the mnemonic mucus subways must be served. I don't know why, but like I just came up with it and it stuck in my head and I've never forgotten the layers ever since. So mucus, obviously mucosa, subway, submucosa, must is muscularis, and served is serosa. You should also know what's inside some of them, especially the actual plexuses. So subways, submucosa contains the submucosal plexus. Must is muscularis. It contains the myenteric plexus. Okay, so those are the main things you need to know. Now, when we're going to go through these slides, I'm just going to go over the main bits of the gastrointestinal tract and things that really are like stand out about that particular organ. Not like every single layer and what's inside it, but the things that really are important for you to know. So for the esophagus, the epithelium is super important. It's stratified squamous. Again, as I mentioned, because you've got food just entering, there's a lot of stress on the cells there. So it needs to be quite stretched out to be able to deal with that stress. So the stratified squamous cells, it contains some mucus glands within the submucosal layer. The interesting thing is that once it gets to the gastroesophageal junction, so when it joins up with the stomach, it changes into simple columna, because in the stomach, you've got bigger cells, right? However, in Barrett's esophagus, you can actually have metaplasia at this gastroesophageal junction. Generally, the reason why that happens, and you'll cover this maybe in histology or somewhere else, you have acid reflux. So the acid actually from the stomach comes up into the esophagus where it shouldn't be. And because the esophagus just has stratified squamous, which isn't designed to cope with that sort of acidity, those stratified squamous cells become metaplastic and they change into some more simple columnar cells. In other words, you can think about it like the cells within the stomach start to grow into the esophagus because it needs to deal with this acid that is in a place where it shouldn't be. However, metaplastic cells are not the best because while they can actually cope, like they're supposed to be there to adapt to this change, they're also very fast growing. They're not supposed to be there. And so there's a huge risk of it actually becoming dysplastic and then neoplastic. So in other words, you start to develop an esophageal cancer. So this is a really important pathology thing to just understand. It's called Barrett's esophagus. You'll see it come up time and time and time again. And there's a lot of other risk factors, but the main ones to understand here are acid reflux. And then the muscularis externa layer transitions from skeletal muscle a little bit higher up to smooth muscle a little bit lower down. So higher up, it's more voluntary swallowing. Lower down, it's involuntary swallowing. In the stomach, the reason why it's pretty much the only reason why it's more interesting than other organs or other organs in the GIT is firstly because it has a huge amount of really acidic contents inside it. But secondly, because every other layer contains only, every other organ only contains 2 layers, the circular and the longitudinal muscle layers. In this case, you've actually got 3. So you have, again, the same thing, circular, longitudinal, but you also got oblique fibers. And that the reason why you have that is because it needs to churn sort of like out to in, like balloon out and then balloon back in 3 dimensions. Okay, so as to get the maximal churning. Other things that are unique is that the epithelium is simple columnar. As we kind of mentioned previously, it has a bunch of gastric pits, and those gastric pits become gastric glands. What do those gastric glands contain? You might have covered this in physiology when you look at sort of like PPIs and stuff like that, but you've got parietal cells, chief cells, mucosal cells. That's it, right? And I've got like a zoomed in version of those gastric pits just for you to see. You don't need to differentiate between the 3 types of cells. We just know that if you get a picture that looks like this, it's probably going to be something in the stomach. You also got the small intestines. So this is just a very general structure. I'll go into specific parts later. So generally speaking, small intestines, epithelium is simple columnar. Again, as I mentioned, because a lot of absorption is happening. Over here, it's more going to be nutrients. When you look at the large intestines, it's more water. The surface, if you actually try and zoom in on it, you'll see that at 3 levels, you have the surface area being amplified quite a bit. And of course, this makes sense because this is where absorption of nutrients happens. So you want to absorb as many of the nutrients as possible before that food gets pushed out. At the first microscopic level, you've got the plicae circularis, which is just the folds within the lumen. So you would have covered this in anatomy. It's an easy way to differentiate between small intestines, large intestines on X-ray. You also got the villi. So zoom in a bit more, you've got villi, which are the finger-like projections, which you can see in this diagram here. So these big fingers, they're your villi. And then if you zoom in even more, you got the microvilli. So something that you can't really appreciate here. But if you look at individual cells and you look on their borders, they've got, again, really small finger-like projections that come out of them. Hence why they're called microvilli, so smaller versions of the big villi. And another term for it is brush border, because that's pretty much the interface at which the nutrient absorption happens. You've also got crypts of Lieberkühn. So kind of like the crypts of the stomach, so the gastric pits and that kind of thing. These are invaginations, and they also contain important cells like the chief cells and parietal cells of the stomach. These ones are not important to actually know though. So like one example would be the Paneth cells. They produce antimicrobial peptides. Again, still an active form of research, and it's not important for us to know. You've also got goblet cells, which are in the submucosa, and they produce mucus. So essentially, whenever you produce mucus, it's usually to allow for passage of food more easily through the lumen. Now, if you look at the actual different parts of the small intestine, because we know there's 3 parts, right? You have the duodenum, which is the beginning. That's where you have these special glands called Brunner's glands in the submucosa. They secrete the alkaline mucus. Again, it's just really logical because you are just coming out of the stomach. The acid is also a little bit of it's coming out into the duodenum. In spite of the fact that there's a sphincter there, some goes through. So you need the alkaline mucus to be able to neutralize that away. So that's the Brunner's glands, which you can see in the diagram at the bottom. The very bottom, you can see the label. In the jejunum, the important thing here is that it just has really extensive plicae circularis. So you can see really long tree-like plicae circularis. And the reason why is because the jejunum has the most important role for absorption of nutrients out of all these 3 sections in the small bowel. In the ileum, the villi are really small. And that's the reason why is because the ileum doesn't really participate a huge amount of nutrient absorption, despite what we all think about the small intestines. The main thing that the ileum does is actually a lot of immune roles. And so you've got these things called Peyer's patches, which are really, really easy to see on histology. If you get a picture like this, where you've got like a wall of a particular lumen, and it's got these really dark patches on the outside, as the name suggests, Peyer's patches. So they contain a lot of lymphoid tissue to deal with infections of the gut. Let's move on to the large intestines. So as I said, again, they're simple columna, but this time instead of nutrients, they absorb water and salts. On the surface, you don't have villi like you have with the small intestines, but you still have a couple of crypts. Again, not that relevant to know the kind of cells that you'd find in them, but it's just cool to see that there's a similar structure in the small and large intestines. The external muscle layer is also interesting because it's very thick compared to other parts of the tract. And it has its own sort of discrete strands, which are known as taeniae coli, which are those like 3 sort of muscular bands, which wrap around the entire, like they start at the appendix where they converge, and then they come out, branch off throughout the whole large intestines before they reach the end. And it's what gives, sorry, I should mention, it's what gives the large intestines the haustrations, because when they contract, it leads to, there's no easier way to say it, leads to the haustrations. If you have a look at a diagram, it'll make sense, right? They kind of, the large intestines sort of clump together. Goblet cells, again, similar to before, they just produce mucus to ease the passage of stool. It's more important here because you are absorbing water, right? So your stool is starting to become a lot more hard. You need an easy way to be able to push it past. Otherwise, you're going to get constipation, which is not good. And then you've got the anorectal line. So I've put a little diagram at the bottom here. So the distinction between the anus and the rectum is that you've got columnar cells within the anus, and then they go into the rectum, which is stratified squamous cells. Okay, oh, sorry, the other way around. Rectum, columnar cells, and then it goes to the anus, which is stratified squamous, because it's pointing out into the open world, right? So it needs to be well protected from the environment, whereas stuff on the inside is more about absorption and stuff like that. So it can be columnar. Now we go to the liver. This one gets really confusing really quickly, but try not to get too confused because it's not very high yield. Just remember that the liver is composed of hepatocytes, so cells of the liver. They have a lot of metabolic and storage functions, and they tend to be arranged in hexagonal arrangements, so in groups of 6. And these hexagonal, so they call lobules. So you've got 6 portal triads, and I'll go over what a portal triad is in a sec. So you've got 6 portal triads. In the center of the portal triad, they're all drained by this one common central vein. Central vein then drains into the hepatic vein, and then they drain back into the IVC, and so on. Another way to think about it, so this is called a classic lobule. There's also this thing called a portal lobule. So I encourage you to look at this bottom diagram here, where you've got this green triangle. And it's just another way to think about it, right? Like it's another perspective. So instead of a hexagon, you have a triangle. It joins up 3 central veins, and in the center of it is a portal triad. So a bit of geometry there, right? So it's the same thing, except now the portal triad becomes the focus of all the attention. And then finally, you've got the hepatic acinus or acinus. I can never tell what the correct pronunciation is. And it's that really colorful thing on the very right-hand side of that diagram. So essentially what we're doing is we're taking 2 portal triads, drawing a line between them, and then we're drawing zones in different layers past that line. So closest to the line is kind of green, and then you go orange and then red and so on. Generally, lines that are, or zones that are closer to that line tend to participate in more exchange of nutrients. Just a fact, okay? And the further out you go, the less they exchange nutrients. Now, between the hepatocytes and the sinusoids that actually join up the portal triad with the central vein, you have these things called spaces of Dicey, which I'm not sure if that's actually shown in any of these diagrams, but just imagine a space, and that's where a lot of absorption happens. And then a couple of random cells, which I remember seeing in a workshop, but it's honestly not that important. Stellate cells, they're also called ito cells. They're involved in liver fibrosis. And then you've got specialized macrophages to eat up any toxins, which are called Kupffer cells. The portal triad, as I mentioned previously, is in this little small diagram at the bottom. And remember, a portal triad consists of 3 main things: a branch of the portal vein, a branch of the hepatic artery, as well as a branch of the common or the bile duct. So the easiest way to tell which is that the biggest thing you can see, which has a really thin wall, is going to be the vein. The next biggest thing is going to be the artery. It has a thick wall. And then the thing with the really thick wall, but a small lumen, is going to be the branch of the bile duct. It's the easiest way to remember it, and it's the way that I remember it. And then finally, to end off on an easy note, the pancreas, we got the exocrine and endocrine bits. Remember the exocrine bits? are the ones responsible. The exocrine bits are the ones responsible for releasing enzymes to digest food. So the way that it does it here is that they have acinar cells. They make digestive enzymes that store within zymogen granules, zymogen meaning inactive enzymes. And you can also see some ductal cells, so labeled here as duct, which secretes bicarb, which is really useful for neutralizing some of that stomach acid when it gets down into the second part of the duodenum. You also got the endocrine part, which is the islet of Langerhans, essentially. It contains the alpha, beta, as well as a couple of extra cells. The main function is to secrete insulin and glucagon to control blood glucose levels, amongst other things. The cool thing is that the endocrine part, it only makes up about 1 to 2% of the mass of the pancreas, but it has way more vascular supply, autonomics, and fibers. And again, that makes sense because these are hormones, right? They need to be released out into the blood to all the cells in the body. So it needs to have a lot of vascular supply. It needs to have a lot of information feeding it into it via nerves. So this all makes sense. And that's pretty much it. So hopefully that was instructive. There's not too much, like I only focused on the pancreas and the liver for the accessory organs because they're the only ones that we really covered and the ones that you need to know. You can have a look at the gallbladder if you want. Another really good one to just keep in mind is the spleen, because it has a way of dealing with encapsulated bacteria, which I've seen come up as a question once. You got like the white pulp and the red pulp, that kind of thing. But really the main thing is the liver and then the other parts of the GI tract. I hope that was helpful. If you do have any questions, as always, please feel free to reach out to me and anyone else in the team. Best of luck for your studies and your exams, and I'll see you in another lecture. Bye-bye.